All right, so let's start then. Uh, so the objective of today's class is to go through various distributions and understand maybe the relationship between them and different other things. Okay, so I'll come to Bernoulli distribution a little later. We'll get back to our binomial distribution, and from that we will see how it kind of gets closer to the normal distribution. Okay, so let's get back to the code that we had the other day. Mm, so okay, so the other day we saw that we can have binomial distribution, and the binomial distribution have some probabilities, right? Which goes, I mean, I'm using the histogram, but ideally it will be a probability mass function, right? Which goes something like this, and then there's symmetric uh, around a particular mean, right? And that's how it goes, right? So you are fine with this? You had this is fine till here, it is fine. Okay, so now yes, that day Lavita had asked a question. I mean, can you kind of combine the two in the sense that binomial uh, and the normal distribution? Okay, so let's see what we had the other day, and then we'll proceed further. So let me just execute this, and then I'll explain it. Okay. So what I've done is I've plotted. I've taken n is equal to 100. Probability of a coin toss, let's say, right? 0.5 for heads. Then I'm doing a p binomial wherein I'm doing 100 coin tosses, right? And then I'm getting the probabilities of a 0 heads versus 100 heads and all the way, right? So this is what I'm getting, 0 to 100 here. Now, I have done a line plot here. Let me do a histogram plot, right? So you get a, or rather, uh, H, okay? So, no, it's not a good idea. This is too close to, what I'll do is I'll change the limit. Okay, I'm changing the limit here. So this is what it looks like. Instead of the line, what can it be? Bar, right? Yeah, bar plot. Not even a bar. What is it? Basically where I get the straight lines. Many of you have a clue what is the uh, type that I need to give for that? No, I think vertical is nana. Let's just ask for the type. Line both H for histogram, S for staircase. Yeah, that's going to give us a line plot. I don't want a line which is connecting lines. Yeah. So I think, yeah, you're right. Hopefully, well, let's see what kind of a, yeah. So no, I wanted a bar kind of a thing, right? A line going all the way down here, touching the uh, histogram kind of a thing. Yeah. So, anyways, so basically you get an idea. So this is what we get using a for a binomial. Know that this is a probability mass function, not a probability distribution function. All right, and that's why it's discontinuous at places. So it'll be 20, 21, all right, 22, 23, and so on. So each of these is for one particular value. So rather, maybe let's say, let's do a point, and then let's make this PCH is equal to 20, right? Really small ones. Yeah, so we get these points. All right, so this is what we're getting for the binomial. Now, how do you approximate a binomial with a normal distribution? Okay, so if you look at this code here, what I'm saying is that binomial is equivalent to a normal given that the mean is given by n into p, right? Which is fine, right? N is the number of data points, right? The number of times I toss the coin, and p is the probability of getting a heads. So effectively, that's going to be the mean anyways, right? N into p. And then what's going to be the standard deviation? Standard deviation is given by square root of n into p, sorry, into 1 minus p, all right? And the square root of, so n p 1 minus p. I don't think you can see this clearly, right? Something going wrong. Give me a second, huh? Let me reconnect my Sketchbook Pro. I'm quitting it. So don't save. All right, let's see, restart. Hmm. Okay, so 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 the approximation will be given by p into 1 minus p into n, all right, and the square root of this. So this is what I'm going to be using. So I said let me have 1000 uh, random variables, okay, which are generated by a normal distribution given the mean is equal to n into p, where I get the p and the n from here, and square standard deviation as this, all right. So now as I execute this line of code, let's see what we get. Okay, wait, I need to execute all of this. Select it all. Okay. Okay. So if you notice, now the green dots were already there, right? And then the dark red line is what I've drawn now. Now the green dots were using the binomial, and the dark red is coming out using the normal distribution. I use the density function to kind of plot it. So that's how it goes. So if you notice, they kind of match each other completely. And if you were to increase n, the matching becomes even better. But in this case, what we are going to do is we're going to make the n smaller, and let's see how it changes. All right. So even for n as low as 10, we're getting a pretty neat distribution here. Let's make n equal to uh, let's make this histogram, and n is equal to, rather what I was interested in, the bar. Okay, n is equal to 5. All right, so I take this and we'll plot this. Yeah, so you notice that This is how we get it, right? With large values of n, for sure we're getting a very neat curve here. Yeah. So this is for n is equal to 5. If we have n is equal to 500, let's see how we get it. Yeah. So is this fine? So is it clear how we're getting it? For a large n, what happens is the distribution is getting closer to the mean. Okay. So if you notice, the standard deviation is square root of n. So as the n increases, the mean will be still at n, right? N into p, basically n by 2. Whereas the standard deviation is getting square rooted, and therefore it's becoming narrower and narrower. Is this part clear? Yeah. So this is what it is. So basically, as n tends to infinity, your binomial distribution tends to normal distribution. So just like in the last class, we said binomial distribution is a very natural distribution. It exists. Similarly, normal distribution is a very natural distribution and it exists. In fact, for anything that we pick up, right? Any data that we pick up, it is very likely that that data would have normal distribution. All right. And if we end up assuming that it was any other distribution, if we end up taking mean somewhere, right? So we ended up adding some of the values and take a mean, and then we take a distribution of those means, that for sure will be a normal distribution. That's what we saw in the previous classes. Are you with me on this? Correct? If yes, please raise your hands. Any question on this? Okay. Yeah. So know that binomial distribution and normal distribution become the source of almost everything else as far as distribution is concerned. Okay. Let me just change some of the things here. It's my Wacom which is not working properly, looks like. Pen mode. Basically, I don't know, when I'm connecting online, that's when this laptop keys weren't working. Okay, fine, doesn't matter. You can just use the chat. Lavita is not able to type using her keyboard. Her keyboard is having a problem, so she's chatting with me on the WhatsApp. Okay, all right. So this is done. Now, what I'm doing is, so we're changing the values of n, and we're seeing this, the same thing here. Okay, so let me just send you this code. Okay, will you guys do me a favor? Like, I have a lot of code, but I want to focus only on some of it, and therefore uh, can you kind of compile it for the remaining classes so we can use that same code for the other people? uh, I think there was another question the last time, that is, if we increase n, how does it change? All right, so I'm going to so for the first is, say, let's okay. uh, so let me reduce this. Okay, let's do it for a simpler case. N is equal to 50. So I'm doing this, and then I'm doing another one with n is equal to n by n into 3. That means 150, right? And then let's see what happens, how things change. So I'm plotting that as well. Okay, so there we go. Okay, and let's do a control 3. So what is happening here? We have 2, that's fine, but this is showing up as a red line. What is that? This was supposed to be something which was what? Okay, tell me why. Why am I getting a red line there? Will be a little difficult to. Why am I not getting a? I should have got something like the bar lines that I got earlier, right? I did a binomial distribution for n is equal to 150, and suddenly I'm getting these red lines rather than actually seeing a distribution. Can you see the graph and tell me, is there something wrong with it? Or if at all, what is wrong? Or whatever it's showing is correct, just that it is not showing something. Yeah, because I really want you to understand this. So Kameshwar, you can talk back. Just two of you, right? So why don't you just speak back? And Lavita, maybe you can type back. No. Okay. What? What after 20? No, we knocked off the cumulative part, right? We already did p binomial this minus p binomial the previous value. So what is the reason? Look at it carefully. What has happened? Let me just do it step by step. All right. So I'm doing it just for this much part first. Okay. I'm not drawing another plot, but I'm actually calculating everything. Okay. So this is what we got. Now I'm drawing this plot, which is p-value 2. Which are the p-values 2? It is based on n is equal to 150. All right. And I'm drawing a line plot. Okay. And my color is red. So when I plot this, I just seem to have getting a line which is at a 0 point. What's happening here? Got it? Okay. So it you may get lost. Basically, what's happening here is this is up till 50, right? And now this is up to 150, and we noticed that when it was till 50, then also all the values were kind of lying between 10 and 40. There were no values between 0 and 10, right? Hardly any values. It is the same thing that is happening for a plot when it is up to 150. A lot of the values would be lying near around 150, which means around 140 to 160 maybe, right? Everything else will be tend to be 0. So 0 to 50 is all 0. That's the reason. What do we do then? Let's change our previous plot. I say the main plot is what determines our x limit, right? So I say let my x limit be n into 2. Let's see if that helps out. So I take n is equal to 2, okay, and then I plot. Good. So I'm getting now, right? So do you see this? What's happening? So this is what I get. So this is for the second binomial. Basically, n is equal to 150. Wait, what happened? 150 should have got us. Yeah, 150 will get us a mean of 75, right? Because it is 0.5. Clear? So yeah. So then if I was to clear, no? So basically the green one, let me change it because you'll be slightly confused. What I'll do is I'll make the type of it as not line but histogram. All right. So these two are histograms, right? So the red one and the green one, they are the histogram. Let me make it exactly the same as it is. PCS is equal to 20, line type is equal to 1. Yeah, line type is equal to 1, PCH is equal to 20. Okay, so let's just do this. Yeah, so is this clear? So what's happening is as we increase n, of course the mean has to shift, right? The mean will become n by 2, and correspondingly then we have a standard deviation as well. And then same thing I do, I also want to plot the binomial distribution corresponding to this. Okay, so how do I go about it? I just pick up maybe this formula. Okay, I copy it here, and I need to make necessary changes. Instead of n, I say n2. All right, and instead of p2 p, I say p2, and then n2 p2 and p1. All right, and let's see what we get. So I pick up this line of code and I print it exactly, right? So I'm getting another binomial here. Sorry, another normal distribution which kind of matches this one. Is it clear? So are we in sync about the two? I see some gap here, but I don't know why that is there. Uh, Square root of n2 into p2 into 1 minus p2. Perfect. All right. Anyways, but we can say that we are able to approximate binomial with a normal distribution when n is a decently large number, right? So good enough, right? So now you're also clear about so let's come to normal distribution now. So having said this, now let's start playing around with normal distribution because that's going to play an important role. Okay. Uh, hmm, Okay, so now we know that for a normal, this is what we have studied a lot. Then a normal distribution, your curve will be defined by two parameters. One is the mu and another is the sigma, which is the variation, right? So now what is interesting about a normal distribution is, say I get some distribution, right, which is given by x, right? So x and this is the probability density function, right? So if I was to do x minus mu, what happens by just by this much, right? All the values I just shift them by mu. What happens then? My whole shifting is such that this will become centered around 0, right? So I get it centered around 0. The next thing is, what is standard deviation? This is like how far it is away, right? So if I divide this by standard deviation, my data gets centered around standard deviation is equal to 1, right? So basically this x minus mu upon sigma, we call it a standard normal distribution. We have a normal distribution, but we have standardized it, and typically it's denoted by z. All right, but I mean, don't bother about the z part. Just know that x minus mu by sigma becomes my standard normal distribution. All right, so uh, mm, so what we will do is, let me kind of show you this, the standard normal distribution part. Okay, how we'll do it is, I'm going to generate random numbers. All right, and we will plot them. Same thing like here. All right, so I say plot density r norm, and let's say I plot 1,000 points, and then my mean is equal to m. All right, and standard deviation is equal to s. All right, and before that I say m is equal to 10 and s is equal to 2. All right, so I'm doing this. Let's execute this. Okay, so if you look at the plot, so we get a plot something like this. Okay, so now rather than the density plot, let me do a histogram. uh, okay, uh, in the histogram, let me change the bins is equal to 100. Let's see, let's make more data points. Okay, so wait, yeah, right. So I'm creating it more. All right, so you can see that's a neatly made out normal distribution, okay, with about 100k points. Okay, now what I'm doing is, notice this, the scale, right? So there's a frequency here, and this is what we get here. Now uh, yeah, so what I'm doing is, I'm changing the frequency will remain the same, but notice that it's centered around 10, from 5 to 10, right? 5 to 15. What if I make my mu is equal to 0? All right, let's see how it looks like. Exactly almost the same curve. The only difference is that it's now between -5 and 5, right? Just to ensure that everything is the same, I say set dot seed 0. or 1. Okay, so which will ensure that the after that whatever random numbers are generated will be the same all the time. You see, so every time I'm executing it, I'm getting the same. Now what I'm doing is I'm making the mean as 10. Just notice, is there any change in the curve? Tell me, what is the only thing that has changed in the whole curve? Oops, what happened? Lavita not there. So tell me, what is the only thing that has changed, Kameshwar? I will redo it. If you notice the curve, I'm replotting it. Okay, exactly, and nothing else changes. Notice that, right? Now another thing that I do is I make stand. So that's the only thing. Now standard deviation instead of 2, I make it 1. Let's see if there is any change. Okay, do you see what is the change? Only the scale. Let me make it 10. So it is only the scale that is changing, but the plot shape is exactly the same actually, right? So effectively, can we say that actually we have just one distribution? It's called standard normal distribution. Understood, no? So there is only one normal distribution, which is called the standard normal distribution. From that, we are able to create many by one is creating the mean, wherein it gets shifted by that much, offset ho jata hai, and then we create a standard deviation number, which is again the scaling of that same. So understand that there is no actual distribution in the slope or anything of the curve as such. It's the same shape. If I was to, normalize it, clear on that, standardize it rather. It's a normal distribution. It's a standardized normal distribution. So effectively, if we just focus on one standard normal distribution, we have understood all the other normal distributions also, right? Okay. So this is about the normal distribution. Only just this much. Yeah. Yeah. No, I can't hear you. Huh? Yeah. Tell me. Yeah. Yeah. Tell me. I can hear you. Yeah. 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 Let's instead of yeah. Yeah. It'll be pretty neat and smooth curve. What I will do is let's just make a small change. Okay. So what I'm doing is I pick up the histogram here. All right. I say A, correct. All right. I say my histogram values are given by this equation. Okay. And then what typically happens is, let's just do this much. Okay. And then I say HV. All right. So we'll see some values coming up. So in the HV, I have the density curve here, right? So dollar density. So what I will do is I'll plot the dollar density, or I can even do the counts. Okay, so whichever way, both are fine, right? So I can say HV uh, dollar counts. All right, I want to plot this. Okay, let's see what we get. Do you see this? So I'm using. So if I say type is equal to L, all right, so it'll be a line connecting each other. Got it? Are you there, Kameshwar? Yeah. So yeah, so this is basically the same thing. That's how you can draw it from the histogram. Now if you keep changing, let's say what we need to do is uh, say if I reduce the bins, right, let's see what we get. It'll be more discrete, right? So if we increase this, yeah, if I increase the number of random variables, becomes even better, smoother, right? So I took a million random variables and I created a histogram of that, and then I plotted the based on the counts. Yeah. So clear, no? This is what your question was, no? Right? So instead of counts, I can do density, uh, or an easier way to do density can be also if I just, all right, so let's do this. So the only thing that changes here is the scale, which is nothing but count divided by the number, right? So if I say count divided by the total number, which is in our case 10 raised to 6, right? So we get the same curve. So absolutely the same curve that we got with density is what we're getting now, right? So that's it. So this is the key thing about a normal distribution. So now, what does the normal distribution tell us? Now let us try to understand that, right? So and then we can kind of proceed further with things. So wait, let me just try to contact Lavita. You trying to contact her? Okay. So this wait, let me just try to reconnect my, I don't know why there's a lag when I have the, what happens, what creates the lag. Let me see if the other software also has the same lag. Is she coming? Okay, then we'll not bother. We'll continue. But this was really important stuff, like say. Anyways, I think we'll continue. Uh, so let me explain another distribution to you. Before that, let's just look at the PDF file as well. Okay. So Bernoulli I will come to. Binomial trials we have already seen. Okay. Normal distribution we've seen now, right? So we're saying, okay, so we get the standard normal distribution. Normally it is denoted by Z, as I said, right? When mu is equal to 0 and sigma is equal to 1. Okay. So this is what, so these are just the numbers we are already aware. 68% lies within one standard deviation, right? I will explain that concept, right? Uh, yeah, I was just quickly going through it. Okay, so let me explain this thing about standard deviations. All right, so we have a normal distribution. Okay, now for simplicity's sake, we take mu is equal to 0 and sigma is equal to 1. All right, now what is this? It's a probability density function, and this is x, right? What are we saying? When we say the probability density function, which means the integral of, right, this probability density function, let me denote it by some f, right? F. All right, so it's an f of x. Integral of this f of x dx from minus infinity to infinity. What's the value of that? Yeah, right, because that is the total probability. Overall probability has to be 1, right? Now because normal distribution is symmetric around the mean, therefore up 0 minus infinity to 0 will be how much, right? So that is 0.5, right? Now if I take some point here, I say let me call it x1. What is the probability that the value is less than equal to x1? What are the chances that I will get a, say if this is the distribution, what are the chances that the value that I get out of this distribution randomly will be less than equal to 1, because these are negative numbers, and that's why I'm saying less than equal to 1, right? So are you getting this? So they'll be denoted by what? The area here, right? The area from x1 to minus infinity, right? So the yeah, so basically normal distribution, let's say a distribution function, we were talking about the probability, sorry, we were talking about the normal distribution, right? What I'm saying is, let us assume that there is some data which follows the normal distribution. Its probability density function is given by the normal distribution, right? If that is the case, then oh, Lavita has no internet. So so if that is the case, right? We so I mean the whole concept of everything to do with stats and inference is this, that we assume most of the times that our random variable is such that its probability density function is given by normal distribution. Okay, if we are saying that, then we are saying that x is our random variable, right? Or rather, this is the distribution, and I generate a variable which is say x1, right? So x1 is pulled out of that population set. Okay, now what is the probability that this x is less than equal to some x1? Normally this is how I denote a random variable, right? So what is the right? So this probability will be given by the area from minus infinity to x1 for function fx into dx, isn't it? So this is what it is. How can I quickly get this? These are what is called the probability distribution tables. So so normally earlier, because the softwares were not there which would have these tables, people would look at the, all the statisticians would have these tables, and that's how they would solve things, right? Now in R, what do we have? We had R norm. What is R norm doing? R norm is generating the random variable. Okay, generates a random variable based on normal distribution. What then? There's another function called p norm. So what is p norm doing? P norm gives me this probability. So if it is supposed to give me the probability, what all are the inputs for p norm? If we go back here, the input is x1, right? So I say p norm x1. I would get the probability. So let's try this. I say what's the probability p norm. So tell me what's the p norm for 0. Yeah, sorry, just check it up again. P norm for x1 equal to 0. What is p norm? Is the probability under the curve from minus infinity to x1. If x1 is equal to 0, what is p norm? Huh? Yeah, 1 by 2. Exactly. Wait. Lavita is facing some problems. Yeah, that's what she's writing me also. Why is that happening? User should not be misbehaving. How short soft? My concern is software should not be misbehaving. Okay, now what do we do? I can see the Vita now. I think she's able to log in. Good. All right, got it. So this is what is the key thing here now. And our focus is the whole of the statistics revolves around this probability given by this function. All right, which we are able to capture using p norm. Now, what is the probability p norm for -1? Maybe you don't know this, right? We have to compute this, right? What are we saying? We're saying this value is -1. What's the area under the curve here? Let us look at that, right? I said p norm -1. So I get 0.1586, which means about 15.86%, right? So that's what it is. Now, uh, so what is the probability of +1 then? Can you tell me? If you know the probability of -1, what's the probability of +1? P norm for +1, not probability, P norm for +1. Exactly, right? Because then we're talking about area all the way till here, right? So, and we know that they're symmetric around the mean, and therefore it'll be 0.84, right? So it's exactly, so 1 minus this, right? So remember this, that through the 2 we can get the other value, right? So if I was interested in this area, let's say, right, my focus is this area typically. So how can I get it? I can straight away get it as either as 1 minus p norm 1, or straight away as p norm -1, right? So this area is also equivalent to p norm -1. All right. So this is the key thing here. Wait, already have slides created for this and very nicely done up. Let me just pull out where they are. Let me search. Give me 1 minute. Hmm. Which one have I done it in? Okay, I think I should have done it in. Hmm. This was to come later. Hmm. Mm. Okay, no, maybe there. We have already covered this. Right. So, so we've understood. So this is basically called the p-value, what we saw now, right? So now a straightway jump to another concept, that is hypothesis testing, right? And we will look at what it is about, okay? And with the help of that, we will try to understand. So now let's say yeah, it's called hypothesis testing. Yeah. So now my hypothesis testing and p-values are of interest to me. What am I saying about hypothesis testing? I'm saying that say so what is a hypothesis? It's like, what am I assuming? So I'm assuming that my mu is equal to some mu zero, all right, of the data, and it could be that my hypothesis, alternate hypothesis is called, say h1. I say my alternate hypothesis is that mu is not equal to mu zero. It could also have been mu is greater than mu zero, or it could have been mu is less than mu zero. So I have three choices here, right, for the uh, alternate hypothesis. Or I could have said mu is greater than mu 0 plus 5, let's say, right? So, so now, so now what do we do is we take a sample, right? Say I take a sample of size n. Now the sample happens to have some mu, which is given by mu s, right? And then sample also happens to have a sample standard deviation. Okay, how do we know that that mu that we got is correct, or what is it indicative of, right? So the point is, let's say we had uh, we were to measure the uh, average length of say uh, say the nut bolts, right? Say a company is making these nut bolts, and you want to measure because it's a mechanical process, the length will vary some a little bit, right? So you want to measure that the you want to say that I will pass the nut bolts if the length is at least, say, to some point. Let's say it is 2.55 uh, centimeters. So I'm measuring all the way till 100th of a centimeter. All right. So, and that's what the company has told me. All right. So they say that we produce nut bolts, which the length is minimum length is 2.55. Right. Now, what happened is when I took the sample is giving me the sample mean size as 2.54. And then there's a sample standard deviation, which is given by, let's say, 0.01. Now, can I say that the sample, there is a possibility that the sample is still for a value which is 2.55. Are you getting what I'm saying? Let me rephrase my question. Let me insert a page here. Yes, I'm repeating this concept, right? So what I'm saying is, say I'm an inspector, and in the factory they produce nut bolts. Okay, and these guys tell me that the nut bolts that they produce have a mean length of 2.55 centimeter. All right, and they say that there is some standard deviation, which is, let's say, standard deviation is given by uh, a value of 0.02. Okay, so this is what they say, that we produce this. All right, now how do I test it? I go to the company, I pick up a sample of the nut bolts that they're producing, right? I don't want to spend too much time. It takes me too much time to measure the length of each of these with a vernier caliper all the way till the 10th of a centimeter, right? 100th of a centimeter, right? So I need to use the vernier caliper for that. So I say, okay, look, I will have an end size which is equal to 30 maybe, right? So I don't want to spend too much time. Size is 30. All right. So I take a size of n which is 30, and I get all those values. I ended up finding that my mu sample is 2.54. Okay, and my standard deviation of the sample, okay, so I denote it by S, is 0. Let's make this 53. All right. Okay, so 2.53, and this has 0.01. Okay, then clearly, I mean, looks, just by looking at it, we can say, maybe we need to reject it, but, or we say some values there. Now the point is, if I was to say that I allow 50% margin of error, 5% margin of error, right? Which means that only 5% chances are there that when I take the sample, my answer would go wrong, right? Or the point that I'm saying is that let us assume this is my actual distribution, right? This is mu 0. Okay. Now there is a probability, right? There are chances that the sample that I take ends up being falling here, all the 30 samples, right? And such that this value is, let's do it the other way, this size, right? So this is 2.53, and everything is centered around here. Are you getting this? Around that, or values around this. All right. So I'm getting all my values around here. Okay, and the mean is this value. Now, what is this probability? I need to find out that. Okay, if this probability of getting the values in this region, all right, is greater than the error margin, which is like in my case 0.05, then I'm saying with some confidence that okay, this is fine because I have an error margin only of 0.5. But if it is less than that, right, if that probability comes out to be less than that, that means, oh man, the chance of that is happening is very less. So it was only 1% probability that this kind of data should be coming, let's assume, right? In which case, what, my margin of error is 5%. So I'll say no, I don't accept it, because it is less than the margin of error. Suppose this was coming out to be 6% chances, right? Assuming my null hypothesis is correct. Are you getting what I'm saying? Assume that data still has mean is equal to this, which means if I had taken instead of 30, maybe if I had taken 300, chances are that I would have got this kind of an answer. What's happened is that the answers that I got, they were all bad ones, and that's why I ended up having this. Have you understood the question clearly? Because this one question explains everything else that will come further for the hypothesis. So therefore, understand this well. I mean, just by looking at the numbers, you would say no, company is doing fraud, right? But what I'm saying is I need to measure the probability of this happening first, and then see whether that probability is acceptable or not. Have you understood the question, Kameshwar, Lavita, both of you? So, okay. So it doesn't matter. We will continue. She knows a lot of this stuff, anyways. Okay. So now this is the crux here, right? I want to find out this. So that will kind of do everything for me. But first of all, first thing is standard error of the mean. So now this data, right, is so what will be the standard error of the mean? It would be given by sigma, this sigma, let's say, all right, divided by square root of n. Would it be given by sigma by square root of n, or would it be given by s by square root of n? Huh? I want to find out the standard error of the mean. See, I got this mean, right? Mu s. I want to find out the standard error of the mean of this. Should it be given by sigma upon square root of n, or should it be given by s upon square root of n? Yeah? Hello? No, I can't hear you. Yeah. So should it be given by sigma upon? Okay, wait. It by definition, this is what it is supposed to be. Okay, and it is associated with sample all the time, not with the population. I mean, when we say standard error of the mean, that means for the sample only. Okay, because there is no standard error in the whole population, right? But when do we use this? We approximate it by this when we don't know sigma. In our case, we know sigma. In this case, we know sigma, right? So therefore, we would take it as this value, 0.02 divided by square root of n. If we did not know sigma, then we would have taken it as s upon square root of n. Is this clear? Okay, let's move ahead. So now standard error of the mean is given by sigma upon square root of n. So when sigma is not known, then s can be used instead of sigma. All right, so I say s upon sigma square root of n. We have already covered this. So now how far is this mu sample away from mu zero? All right, how do we know that? So basically it will be, if we were to consider now, if we were to take the distribution of the, so what are we saying? We're saying these, I'm taking a distribution of the mu samples, right? I'm saying at the basically the samples, and when I'm taking the distribution of the samples, not of the population, right? My null hypothesis is that the mean of the samples should still be equal to mu is equal to mu zero, and then I'm getting these different values for mu, right? And the standard deviation is given by this formula, which is sigma upon square root of n. In this case, it becomes s upon square root of n. Now what I'm saying is, where does this value fall? Let's say this is what I'm getting it as mu s. All right. So now what I want to find out is how far this is away from this. All right. And we have already done this in normalization. No? How do we do this? I say mu s minus mu zero, that is the distance, divided by the sigma, that will make it standardized. Once it is standardized, then this is given by the q value. Let me explain the concept of q value. Okay. So what is the Q value? Um, so we had seen the P norm, right? In this distribution, we said the probability is of X being less than this, right? Probability of X being less than equal to some X1 is given by P norm. What if I know the probability? So it's given by P norm, right? And let me call it P value. And I want to find out X1. So basically X1 is equal to Q norm of P. It is basically the quantile of P. Is this clear? So we have another one, right? How do I, so in case probability is known, how do I get the X1? I say Q norm of P. Yeah, 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 yeah. So till this you were clear, right? The probability that X, which is a random variable, is less than X1. Let's, right? So, oops, Control Z, right? Right? So it's P norm of X1. Now, here we said X1 is known and I'm finding out P, right? What if I say I know P and therefore I want to find X1? In the sense, I'm saying what will be the value of X1 corresponding to 15% probability? Uh, yeah, we uh, exactly, right? So now what I'm doing is this. Let's look at this. I said P norm. So I pass it to a function called Q norm. So Q norm of P norm of 1. What will I get? Exactly, right? So we will get back the same number, right? So isn't it? So it's just the inverse, isn't it? So we've, so this is called quantile, right? So in the Q norm, basically the X1 and so on. So they are called the quantiles, right? So when we have a normalized distribution, we have X1 as 0 here and then 1. Say for a value of X equal to, no, they are percentile. Yeah, no, quantile is a generic term which is used for any kind of distribution, which means, for example, uh, uh, how do I explain? Yeah, say for cat we talk about percentile, right? But for a data which is split into 4 parts, we say quartile. So all of these are basically called quantiles. So we can have a centile or a percentile or a quartile, right? So but they, so that's it. Basically, you're just dividing the whole line into distributions, right? So saying that okay, point one is the point where the I mean, so this is what is, yeah. So if I say uh, Q norm of 0.15 to 0.25, so I get a value which is minus 0.67. Right, so look at the definition. So this is a vector of quantiles basically, right? Okay, so this is the key concept here. One is the quantile and this is the probability. Okay, so if I was to come back to my stuff here, mu s minus mu 0 upon sigma x bar here, the z that I get is a quantile, right? this will be equivalent to a quantile. Basically, it could be minus 6.7, minus 0.67, minus uh, zero point 0.2, plus 0.2, anything, right? This is not probability, right? But there is a probability of this value. Got it, no? So why am I taking it this way? So I can normalize it and standardize it and it becomes easier for me, right? So this is what I did. So Z is in terms of standard deviations of the sampling distribution. Clear? So once I've done this, so now what is the probability of getting mu S? That's my question here. So this is a single value probability and is 0, right? Probability of getting mu S is what? 0, right? Because it is such an infinitesimally small portion. So we say that we have to consider a range, right? So you have to consider a range because that's how it works for PDF. So now what I'm saying is, let's say I can look at 5 different kind of ranges. I say my range 1 is what? Probability of minus infinity to mu S. So basically all the way from minus infinity up till this point. Yeah, wait, I think I will put you into mute and then you can do chat because that will probably get us better voice. Okay. Now, now I have, so I can divide this into different regions. Let's look at it this way. Here, look at it. So let's say this is my range 1. Okay. This is my range 2. All right. Then I'm saying that the range 3 is anything which is not range 1 and range 2 given by the green area. Can you see this? Okay. Then range 4 is given by, let's say I assume that the values are up till minus 3 sigma till plus 3 sigma. Okay. So that's my range 4, let's say. Okay. Then the yellow one or the orange one is minus 2 sigma to plus 2 sigma. Like that I can define my ranges, right? So I have a range 1, a range 2, a range 3 and different ranges that I'm defining. I can define any number of ranges. So is this point clear? Hello? Are you getting this, Kameshwar? Okay, right? So I have defined all these ranges. I wanted Lavita to be there because even she would have gained some, right? So now the range 3 is given by what? I say absolute value of mu 0 minus mu s minus of that to positive of that, right? So that's for how I'm defining my range 3, which is given by this green area, all right? So and so on. So I define my range 1, range 4 as plus minus mu 0 plus minus 2 sigma x bar. Then range 5 as plus minus mu 0 plus minus 3 sigma x bar, right? And this is denoted by around 95% probability. So there is, and then plus 3 sigma is 99.7% probability. So what we are saying here is that there is 95% probability that the value that you get would be within the green area. And there is, within the orange, this yellowish area, dark yellowish area, right? And there is 99.7% probability that it is between the two blue lines because it is up to 3 sigma. All right. Don't go by the graph. I mean, it's not made up to scale, but this is just to give you an idea. All right. So is this clear? So we have different ranges. So some of the ways to say whether mu s is a good estimator of mu 0 are, basically that's what we want to say. Is mu s a good estimator of mu 0? So we use range 5 typically, right? What is range 5? That is 95 percentile area, right? So we say that 95% confidence interval. So if mu s falls within this range, then we can expect it to estimate mu 0. All right, then we will accept the null hypothesis. Otherwise, we will have to reject it. Second way is calculating the p-value, right? So how do we calculate the p-value? So whatever the value of So let's look at the different ways to calculate the p-value. Is it clear so far? So we're adding a new concept called p-value. So our alternate hypothesis can be, there can be three different alternate hypotheses, right? One is that mu s is not equal to mu 0, in which case, as long as mu s falls either in range 1 or range 2, we are saying that it is not, mu s is not equal to mu 0. In case mu s falls only in range 2, then what are we saying? That mu s is greater than mu 0. Alright, if it falls only in range 1, alright, so if we were to consider only mu s less than mu 0, then we have to consider the probability of mu s coming in range 1. Alright, so that is how we will not in blue range, right, when it is not in the blue range, okay, either it is outside the blue range on both sides, in which case it is not equal to, or if it is on the left hand side, then it is case of mu s less than mu 0. If it is on the right hand side, it is the case of mu s greater than mu 0. So now let's say R1 is given by probability that x is less than equal to mu s. Say let's denote it by P1. So now, and if this is less than 0.025, right? Then for alpha is equal to 0.95, right? So if this is equal to 95 percentile, right? Then this has to be what? 1 minus alpha by 2 and 1 minus alpha by 2, right? I'm saying 95% confidence interval and 5% margin of error, which means 5% margin of error means 2.5% here, 2.5% here, right? So which means the probability of this probability P1 should be, so my P value should be less than this. So maximum probability is allowed is 0.025 for me to reject the null hypothesis. All right. Similarly, for range of 2, it is greater than, right? So if less than 0.025 for alpha is equal to 0.95, then mu s is, so that's how it goes, right? So we will look at some examples, it will become more clear to you. Okay, so this is just to explain this, that what is a p-value. P-value is basically the measure here, right? So once you have the z, then we take the p norm of the z, you get the p-value. So that this is just to give you, okay, I think we will stop here. We have a lot covered. What I would suggest is understand the p-value and the confidence interval. Everything else would be clear for you. Just go through this from maybe the notes, etc., or the slides that are there. I don't have any notes to share with you today for today's class, but maybe you could go through the slides, okay, if it is not clear. So because this becomes the basis for all of statistical inference, understanding the p-value and the confidence interval, etc. Because once you know it, then you can solve all the problems. Tomorrow what we will do is we'll look at some of the questions and different examples that will help you anyways. Yeah. So what do you mean by confidence interval? As the name goes, confidence, right? Typically, confidence interval is defined by a range. We say 95% confidence interval, then that means this range. All right. If the values lie here, that is 95%. Or we say 95% confidence interval for h0 is equal to, h0 is such that mu 0 is equal to mu s, okay, and h1 is mu 0 not equal to mu s. In which case, what will happen? If this is 95%, then this region and this region have to be 2.5%, right? Exactly, it is like the tolerance range, yeah. And if I say 95% confidence interval, such that null hypothesis is mu is equal to mu 0 and alternate hypothesis is mu s is greater than mu 0. In which case greater than is the key thing, no? So we will draw it somewhere here, and this is what we are saying. So 95% of the times it should fall here, 5% times it can fall here. So this is for the greater than case. Similarly, less than case would be the reverse of this. I draw this, and then 5% probability that should fall here. Yeah. So that is what. Yeah. Hmm? So we will look at all the different examples out of this tomorrow's class. So that's it for today, I think.